Last class, we have seen a definition for the language accepted by a pushdown automaton. We know that there are two acceptance criteria for a pushdown automata to accept its language. And the first criterion is acceptance by final state, in which case a given input string W is said to be accepted if the processing of W is finished in a final state. If it finished in a non-final state, the input is rejected. That is, in this case, the acceptance or rejectance is decided regardless of the content of the intermediate storage, that is the stack, at the end of reading the input. That is the first acceptance criterion. Based on whether the reading is finished in a final state, the input is accepted or rejected. The second acceptance criterion is empty stack acceptance. In this case, the input string W is said to be accepted if the processing of W is finished in a configuration where the stack is empty. If the stack is empty when the input is finished, then it is accepted, and if the stack is non-empty when you finish reading the input, it is rejected. That is, in this case, the status of the state, whether it is final or not, is not going to take part in the decision of whether the input string is accepted or not. And today, we are going to prove that these acceptance criteria are equivalent. Equivalence of acceptance criteria. And we can have two claims for proving this equivalence. The first claim is that given a pushdown automaton A with a final state acceptance criterion, we can automatically construct a pushdown automaton A prime with empty stack acceptance criterion such that language of A prime is same as language of A. That is, given a pushdown automaton accepting by final state, we can automatically obtain an equivalent pushdown automaton accepting by empty stack. And claim 2 is the other direction. Given a pushdown automaton A which is accepting by empty stack, we can automatically construct a pushdown automaton A prime with a final state acceptance such that their languages are same. That is, here, given a pushdown automaton accepting by an empty stack, we are going to construct a pushdown automaton which is accepting by final state. And in fact, what we are going to do is, we are going to discuss an algorithm which will take a final state accepting automaton and gives you an automaton which is going to accept by both the criteria final state and empty stack. That means the resulting automaton will accept a string by both the criteria, that is both by entering a final state and by emptying its stack. That is what we are going to see in both the cases. Let us go and prove the first claim. That is, from a given pushdown automaton accepting by final state, we are going to construct a pushdown automaton A prime which is going to accept by both final state and empty stack. Consider this initial configuration where the input content is not processed, read head is pointing to the first symbol in the input W, state is the start state of the automaton, and the only symbol on the stack is the bottom of the stack symbol. And recall the syntax or the semantics of the pushdown automaton that a pushdown automaton cannot see any symbol below the bottom symbol. So even if you put a symbol here, the automaton A cannot see it because the automaton will treat the cell with the bottom symbol as the last cell in the stack. So it will never go below it. Please try to remember this, which may need in our proof. So this is the initial configuration given. Hope you remember what a configuration is from the previous lecture. Otherwise, please go and see the lecture again, because it is very essential to know what a configuration is to follow what I am going to say in this lecture. Suppose the given pushdown automaton is admitting this computation for W. That is, from the initial configuration for W, a sequence of steps in the computation takes you to a configuration where the state is a final state. You finished processing your input. The remaining part of the input to be processed is epsilon, and there is a content on the stack. You know that by the final state acceptance criterion, because you finished reading in a final state, you accept, and hence W is an element of the language. Now, given this configuration, if you fire all this sequence of steps, you will get into this configuration is what you are saying. F is your state, you finished your input, so read head is here, and this is the content of the stack. And remember, here we need a machine A prime which is going to accept by both final state, which is done, and also by emptying the stack. Now the question is, to obtain A prime, how will you empty the stack from this configuration? You take this configuration as state F, nothing is there on the input to be processed, and you call this content as gamma. So here is gamma. Now you want to finish the stack by taking out all the simples. So how will you do it? So can I do it like this? What I am going to do is I am adding transition from each final state F in the original automaton. If there is nothing to be processed like this, then you look at the topmost symbol, whatever it is. It is an arbitrary stack symbol. So it could be x1, x2 or anything. You take out that symbol, and that's what I am doing. Okay, without changing the state, you take out the topmost symbol of the stack as long as there are simples. And not that here x is an arbitrary symbol. So x1 means the transition is f epsilon x1, like that. So this will allow you to empty the stack in this particular case. So in this case you are done. The question is that enough? Are we obtaining the required automaton A prime? So what do you think? The answer is no, we are not. So why? Because I am giving you a counter example. Suppose you have this computation for a given input W. I think that this time the input is something else, call it W. And from the initial configuration for W, it goes to this configuration. What is it? The state is P, which is not a final state. The input is completely processed, and the stack is also empty. And the final state acceptance takes this string as not accepted because you finished reading in a non-final state, and hence this string is rejected. So from the initial configuration SW port, if you fire all this transition, what will happen? You will end up in this configuration is what you are assuming. P is the state, nothing is there to be processed from the input, and stack content is empty. Note that now A prime will accept by empty stack because this is what we did to obtain A prime. And now in A prime, remember, this is the configuration. What is the configuration? State is non-final, but the stack is empty. Because the stack is empty, by the empty stack acceptance, A prime is accepting. That is not correct. It's an unsound construction because W was not accepted by A, but it is accepted by A prime using the empty stack acceptance criterion. So that's not allowed. So how can you manage? Do you have any idea to proceed further? We want to manage this problematic case where the original machine is rejecting a string by emptying its stack. That is always possible. because the rejectance or acceptance is defined only based on the status of the state and not based on whether the stack is empty or not. So how will you manage? In fact, there are different ways in which you can do, and I am going to tell you the way the author is telling us to do. Suppose I do this. My problem was when the original machine rejects by emptying the stack, I am in trouble. And to manage it, what I am going to do is, to the new machine, I am going to add a new bottom of stack symbol. This I will set as the bottom of stack symbol for the new machine A prime. And I am going to add a new state S prime to A prime, and I am calling the newly added state S prime as the start state for A prime. And this is the configuration. Suppose I add this transition. What is it? If you are in the newly added state, which is the initial state of this A prime, then without consuming an input, if you have new bot as the bot stack top symbol, then what you do? You change your state to S and replace the new bot with a string of bot and new bot. So if I fire this transition, what will happen? This was the case. S prime, without processing anything, take out bottom, move into S and take in bot and new bot. That's exactly what I did. Okay, I am now into S, and bot and new bot are the content of the stack. And what is this? You can see that this is now the starting configuration for A. Remember that because for A, bot is the bottom of stack symbol, A cannot see any symbol below this symbol. So for A, the configuration is this: S input W bot, because this is not visible to A. Why? Because it will only see symbols until it see a bot. And hope you remember it. And that's it. And now consider the same sequence of transitions which is taking you to this configuration, same previous configuration. The only difference is that below the bot, here we have a new bot symbol, which is the bottom symbol for A prime. Now what you do? Now you can do the previous technique, you add transition. For all final state, what you do, if you are already in a final state without consuming an input, take out the top of the stack symbol, and this time I am adding a new final state. To A prime, I am adding a new state called T, and I will make T as the only final state of A prime. That's what I am going to do. So, if you are already in the final state of the given automaton, what you do is, without consuming an input, you move your control unit from the state F to the newly added only final state for A prime. So you are in T now, and also you are taking out the topmost symbol. X could be any symbol on the stack. And if you fire this transition, what will happen? From F you are changing into T, the topmost symbol is taken out. So now this is the case. See, now you are in a final state, you finished. So you are accepting by final state, and also you want to accept by empty stack. So what you do? From T, you take out all the stack symbols and finish. So add transitions for that. If you are in T without consuming an input and without changing the state, you take out all stack symbols. So you are doing it, and finally you are getting into a configuration where the stack is completely emptied, and so you are accepting by both the acceptance criteria. So you are done in this case, and it remains us to check whether we managed the other situation or not. And not that by firing this transition you will get into this situation where you are in a final state and you emptied the stack and both the conditions are satisfied. Consider the other case. What is the other case? Suppose the input string W was rejected by the original machine by entering a non-final state and emptying the stack. what will happen in the new state? Because it is in a non-final state, finished in a non-final state, by the final state acceptance, this is not accepted. So what will happen? If you fire, you will get into this situation. Not that here the original machine is having an empty stack, but the new machine is having its bottom simple. New boot is there. So it is non-empty for the new machine, and hence when the original machine is rejecting by entering a non-final state and emptying its stack, the new machine is rejecting by both the criteria. It is rejecting by final state because P is not a final state. It is rejecting by empty stack because the stack is non-empty. So we are done, and now this is the time for us to recollect what we did and define the algorithm. So you note that this is rejected. And this is the algorithm. This is what we did. Given a pushdown automaton, we have constructed a pushdown automaton with both the acceptance criteria. Please don't confuse it. I am going to tell you exactly what I did to obtain A prime from A. So what I did is, to the state set, I added only two states. Recall that the newly added state as initial state, and the newly added state which is becoming a final state. So I just added two states, S prime and T, and S prime is going to be the start state. Later we can see. The other change is, to the stack simples, I just added the new bot. Then S prime is the start state of the new machine. I added a number of transitions. Later we can see. And new bot is the bottom simple for A prime, and newly added state T is the only final state for A prime. And what are the transitions? Transitions are all the existing transition plus some more transitions. Which are the more transitions added? You know that from the start state to get into the initial configuration of A, we added this. Change the state to S without consuming an input, and to the top of new bot, you just add a bot. That's what you did. Then you are in the, if you fire this, you are in the initial configuration of A. So all possible computations of A can happen now on the input, and finally suppose the input is accepted. What will happen? Then you will get into a state final. Then you have this transition. For each final state, from the final state F, without consuming an input, whatever be the top of the stack simple, you take out that top of the stack simple and land up in the only final state of the A prime machine. And not that you will definitely get a top of stack simple, because at least this new bot is there. See, why is it so? So for each stack simple, you are doing it. Now you are in T. The stack may be containing more elements. For that we added this transition. From the state T, by remaining in T, you take out all the stack simples. That is what we did. And now you can prove that you can, what you are doing is correct. That is, it is a sound construction. So it's a complete construction. That means if W is a string in the language of A, then W is also in the language of A prime. Why is it so? If W is accepted by A, because it is final state acceptance, you will come into a configuration where a state is final, you emptied the input, and there is something on the stack or nothing on the stack. If nothing there, then new bot will be there, and you will fire this transition and you get into T. After coming into T, you will empty the stack using these transitions. Hence, you are in T and you also emptied the stack, and hence by both acceptance criteria you are accepting, hence this is done. And this is the soundness part. That means if something is accepted by the new automaton, then that must be accepted by the original automaton. Why is it so? If something is accepted by this new automaton, that means you are in T and you emptied the stack. And how can you get into T? Only after coming into F. And if you came into F, that means A is also accepting, and we are done. And that is the algorithm for generating a pushdown automaton with both acceptance criteria from a pushdown automaton with final state acceptance. And now proceed and prove the other. This is the other case. We are taking an automaton with empty stack acceptance and trying to generate one with both acceptance criteria. Here is the input, and from this initial configuration, suppose you have this sequence of steps in computation where it is taking you to a state, whatever it is, final or non-final, we don't know because it is empty stack. You finish the reading input and nothing is there on the stack. Even the bot symbol is taken out. Then by this acceptance criterion, you can say that W is accepted. And if you fire all these transitions here, you will get into this configuration. P is the state, nothing is there to be processed from the input tape, nothing is there on the stack. So now this machine is accepting by empty stack. We want to get it also accepting by final state. For that, what you can do, maybe you can add a new state as final, say T. But how will you get the machine into T? We want to get the machine into a final state. And for that, what you can do? Maybe you can add a transition to make it moving to a final state. But we need a simple on the stack to fire any transition. And that is the semantics of a pushdown automata. Without having a simple on the stack, you cannot define a transition. For any transition, it is depending on the top of stack symbol, and that cannot be epsilon. That is not allowed by definition. So you need to have a simple here. And how will you manage? You can do the same trick. You add a new bot, exactly like what we did in the previous case. And this also is same. So what I did is, from the initial configuration, I did the same thing to move into the initial configuration of the original machine. And now what happens? This is the initial configuration of the original machine, and suppose you have this transition. Then you know that W is in the language, because when W is finished, nothing is there on the stack. Hence W is in the language of A. And if you fire all these transitions from here, you are getting into this configuration where P is the state, nothing is there to be read from the input, and nothing is there on the original stack. And remember here, intentionally we put a new bot. So for the machine, initial machine A, it cannot see any simple beyond this bot. So it cannot see this double bot. For the original machine, it is empty, but for the new machine, it is not empty. Now you can exploit the situation. What you can do is, you can add this. From the state P, without consuming an input, you will have the new bot on the top of the stack. You take out that new bot and you jump into the newly added final state. So you are done. And see here that P is an arbitrary state. Maybe you stopped in some state after finishing reading the input and the stack was empty for the original machine. So in the new machine, you know that because the original stack is empty, now you have only the newly added new bot, which is non-visible for A. So what you do, you utilize that, take it out, and you jump into T, and you're done. And that is what you are doing here. And if you fire this transition, before you will move into T, and you will take out this, and you are done. So you are accepting by both empty stack and final state. And suppose the original string, the given string was rejected by the original machine, then definitely other than this, there will be some simples above it, because the stack is non-empty, means something is here. Then this transition can never be applied, because this will be applied only if the top of the stack symbol is new bot. That will only happen if the original machine emptied its stack. In that case, the original machine is accepting it, and hence what you are doing is correct. So we are done. We are recollecting the steps and defining the new machine, and which is very similar. The structure is exactly the same as the previous case, and the only difference is in the definition of the newly added transition function. The first transition function is also the same as previous, and this is the only difference. The original machine has finished in some state P, then without consuming an input, when the original machine is accepting by emptying its stack, you know that the new bot will be there on the top of stack. You take it out, you jump into T, and that is what you did. And in this case also, you can prove the completeness and correctness. Because of the interest of time, I am leaving it as homework exercise for you to do. And with this, let us move on to the last slide where I am giving you two practice problems as assignment for you to test the algorithm and to understand how how these algorithms are working. First problem, given an empty stack acceptance automaton for this language is given, you are asked to apply the algorithm to construct a prime, and also you test a prime by simulating the computations for these two input strings. This is the problem to test the other algorithm for this language. So today we have seen two algorithms. One is taking a pushdown automaton with final state acceptance and giving you an equivalent pushdown automaton with both acceptance criteria. And the other algorithm takes a pushdown automaton with empty stack acceptance and is giving you a pushdown automaton which is accepting by both the acceptance criteria. And thus, we proved that the acceptance criteria, empty stack and final state, are equivalent. Thank you.